Okay, so maybe we can start. I think everyone is here who wanted to attend. So it is my pleasure to welcome Xinwei Sun. I hope that I pronounced it correctly. He will speak about trustworthiness and basically how to make maybe AI much better. He is currently the researcher in Microsoft Research in Asia. Before that, he did his undergrad in pure mathematics from Nankai University in 2013, and also he obtained PhD from statistics in Peking University in 2018. His focus basically is on statistical models like high-dimensional statistics, causal inference, and so on, and many applications, especially medical imaging analysis. He published over 20 papers in the best journals in applied computational harmonics analysis, and so on and so on. Okay. He's also senior program committee member for NeurIPS, ICML, ICR, AAI, and many others. Okay. So I know we are a bit delayed, so maybe just without further ado, let's start the talk, please. Can you share your screen and?
Okay. Can you see my slides?
Yes, I can see the slides. Yes, that's fine. Okay. Do you prefer to take questions during the talk or basically after the talk? What's your preference?
After the talk works better for me.
Okay. So again, like, enjoy the talk. We'll be listening and asking questions afterwards. Okay, thank you.
Okay. Thank you for the introduction. Hello, everyone. Welcome to my talk. My name is Xinwei Sun from Microsoft Research. I'm very glad to attend this seminar. And today, I'm going to share with you our series of work that from high-dimensional statistics to causality, which move towards the goal of building trustworthy AI models. In the past few years, we all know that deep learning models have achieved revolutionary results in various AI technologies, for instance, the face recognition, the human-machine dialogue system, and imaging diagnosis. And nowadays, it has stepped into scientific findings such as protein structure prediction and drug discovery. Despite this progress, the current deep learning models are not trustworthy, which keep them away from being applied in some real scenarios. And today, I'm going to talk about 4 dimensions regarding the trustworthy issues. The first issue is explainability. The fact that the current black box models are not transparent or understandable by experts will stop them from being in the loop. For instance, in the breast cancer prediction, although the current state-of-the-art method can achieve promising results, but their predictions can be based on some unexplainable information. So this is a concern shared by the radiologists when putting them into clinical practice. Another issue is the robustness, as current machine learning models rely heavily on IID's assumption. So this means even the model fits very well on the training data, it is not necessarily hoped that it can generate well to the test data, which may have a different distribution from the training one. So this non-robustness can cause the serious consequences in safe critical tasks, such as healthcare. And besides for scientific findings, another important issue is reproducibility. For instance, if I find a gene is related to some type of disease, whether my finding can be reproduced in the follow-up experiments is very important because normally these high throughput experiments are very expensive. And also, as current AI models are increasingly being applied by governments for decision-making, so people are concerned about the fairness and the equitable problems. And this is very challenging because instead of equal allocation, the model should recognize that people start from different places. And based on this, the model should adjust their decisions accordingly. For example, the doctor can make different treatment suggestions to patients according to their demographics or healthy status so that they can make sure that everybody has the same chance to be healthy. Okay, so to see what's happening here that causes a problem, we first take a closer look at the current learning paradigm, which first predefine a utility function, which is goal-driven. And it then parameterizes the neural network with parameter theta. And to learn the parameter theta, it uses all the training data, which are assumed to be IID generated from the underlying distribution. Actually, these 3 characteristics are the reasons that cause the problems. And specifically, the goal-driven property of the utility function can overlook the structural modeling of the parameter theta, And even if we do this, there is no theoretical guarantee about the inference of the ground truth parameter on which we have assumed the structural priors. And this is because the complexity of the deep neural network. These two limitations together cause the explainability issue. And for the same reason, it is difficult to implement the false discovery rate control, which can guarantee the reproducibility. And finally, the dependency on ID assumption implies the data-driven learning paradigm, which means the model can inherit some biases from the data. And this will further cause the fairness and robustness problems. To resolve these problems, we resort to a statistical learning paradigm that from high-dimensional statistics to causality. Specifically, we first propose a dynamic approach by differential inclusion and differential inclusion for structural sparsity modeling, and followed by the FDR control in these dynamics. And we then apply this framework to explore the structural sparsity in the deep neural network. Although we find that the learned structure is effective in terms of prediction power, but it can still learn some non-semantic features which are unexplainable. So this in turn motivates us to leverage causality to learn the causal semantic features. And after that, we are starting to explore other possibilities of causality to resolve the fairness and robustness problems. Okay, so this is the outline of today's talk. And due to time limit, I'm gonna mainly focus on the first and the third parts, with other parts introduced briefly. Okay, so let's start off with the first part. And we first consider the sparse regression problem, in which we want to recover the signal beta star from the following generalized linear model, in which the X denotes the design matrix. And we assume the structural sparsity for the signal beta star in the sense that after a linear transformation, the signal is sparse. We denote the S as the support set or the true signal set of the gamma star. And various choices of the transformation matrix D can correspond to different problems. For instance, if D equals to identity matrix, it corresponds to a pure sparsity problem. And our goal here is to recover the sparse pattern and the true values of the signals, which are respectively the sparsity and consistency problems. To see how this structural sparsity can be applied, we first consider the comparative genomic hybridization data, in which the genes are linearly ordered according to their positions in the x-axis, and the y-axis denotes the copy numbers of each gene. And we believe for biological reasons that the nearby genes have similar copy numbers. So we correspondingly set the transformation matrix D here, as the one diffuse Lasso matrix, which assumes there is no difference between adjacent genes in terms of copy number. So the non-zero elements of the gamma or the sparse pattern of the gamma may correspond to abnormalities of some types of disease, for instance, the human cancer or brain tumor. So the recovery of this sparse pattern can help us understand the development of this type of disease. Another interesting example comes from the Alzheimer disease. And in the Alzheimer disease, the patients suffer from short-term memory loss due to the degeneration of hippocampus region, as we highlight in the red region. And in the voxel-based neuroimaging analysis, there are three types of structural sparsities for diseased gray matter voxels. First of all, among all voxels in the whole brain, only a subset of the voxels are lesioned or diseased, because in this case, they are only located in the hippocampus region or other disease-related regions. So here comes the sparsity prior. And secondly, as each region contains thousands or hundreds of voxels, so it is unreasonable for a single tiny voxel to be diseased, while others or its neighborhoods are not. So the spatial coherence means adjacent voxels have similar brain activities. And finally, the diseased gray matter voxels can suffer from degeneration in terms of volume. So we assume that they are negatively correlated with the disease label. If we can appropriately leverage these structural sparsities into modeling, we may achieve highly explainable result. And this is what we have achieved on the ADNI dataset, which is the largest dataset to study the Alzheimer's disease. And by leveraging these structural priors, our method can outperform others in terms of prediction power. But more importantly, as particularly know that the voxels selected by our methods can stably concentrated in two-side hippocampus, while other methods suffer from either selecting scatteredly distributed voxels or redundant regions, which are both medically unexplainable. Okay, so in the next, I will introduce our method to achieve this goal. Before that, we first briefly review the generalized lasso, which is perhaps mostly related to us. And the generalized lasso uses an L1 penalty to enforce the structural sparsity of the signal. It has been previously studied in various forms, such as total variation and fused lasso. But there are two problems for generalized lasso. The first of all, the computation can be very expensive because one have to run several optimization algorithms for each hyperparameter lambda in order to determine the optimal sparsity level. Sorry. Secondly, the incoherence condition, which is necessary to recover the true signal set, can be difficult to satisfy. And we will come back later to discuss it in more details. To resolve these two problems, we propose the following differential inclusion. Specifically, we at first propose a variable splitting term that relaxes the constraint, the linear constraint between the gamma and beta, by introducing another parameter gamma. So the hyperparameter nu here controls the distance between these two terms. Okay. So I will mention later that the relaxation of this linear constraint will also relax the incoherence condition I mentioned earlier. Appended with this variable splitting term to the final loss, we propose the following differential inclusion, which generates a whole regularization solution path for the beta and gamma. If we take a closer look at this differential inclusion, which we briefly call the split Bregman ISS, it is composed of two parts, the update of beta and gamma. And the update of beta is very easy because at each time step, it can be solved directly if you fix the value of the gamma. And for the update of gamma, we first denote the rho t here as the subgradient of the absolute function of the gamma t. And if you see the absolute function, which is piecewise linear, it is differentiable at non-zero points. So its corresponding gradients are equal to 1 or -1, depending on the value of depending on the size of the elements. But at 0 point, it is non-differentiable because the left derivative is not equal to the right derivative. Okay, so it has subgradient from -1 to 1. And what the rho t does is it undergoes a gradient descent flow starting from 0. So as t increases, some elements of the rho will reach the boundary, which is -1 or 1. And this means the corresponding elements of the gamma will be selected to be non-zero, according to the definition of the absolute function and its subgradient. So this differential inclusion can generate a whole regularization solution path, because as t increases, more and more variables will be selected to be non-zeros. So t here actually plays the role of regularization hyperparameter. If you visualize this solution path in which the x denotes the t and y denotes the coordinates of elements in gamma, we can see that at the very beginning, when t equals to 0, no elements will be selected because they all lie at the horizontal line 0. And as t increases, some elements of the gamma will be selected to be non-zeros. And if we continue this process, more and more variables will be selected to be non-zeros. And finally, all variables will be selected. Okay, so this means as long as t is large enough, the algorithm can pick up the information of noise. So we must be careful because unlike the traditional optimization algorithm, which always focus at the final step to analyze the convergence rate, we should not stop at the final step because when the noise is present, the corresponding model can pick up the information of noise. So it will be overfitting. So we'd rather adopt an early stopping mechanism in which we can only pick up the information of signals without overfitting. Okay, so a natural question to guarantee this early stopping mechanism is, do the early selected features actually belong to the true signal set? And to answer this question, we first present an intuition about our theoretical results, that we first assume the irrepresentable condition, which assumes the orthogonalities between our oracle subspace and overfitting subspace. The oracle subspace is a space expanded by the true signal set, and we denote its complementary subspace as the overfitting subspace, because its complementary subspace contains the information of noise, and the model, if the model fits the noise information, it will be overfitting. So this orthogonality, aka the irrepresentable condition, can guarantee that the solution paths first pick up the information of signals and track on the oracle subspace until to the saddle point, which is unique if we further assume the restricted strongly convex. And after the saddle point, it starts to track on the overfitting subspace to pick up the information of noise. So the irrepresentable condition is very important because it can guarantee that the solution paths at first pick up the information of signals. Okay, so formally speaking, our irrepresentable condition is dependent on hyperparameter nu, which, as we recall, is in the variable splitting term that relaxes the linear constraint. And if as nu increases, there will be less constraint between the hyperparameters. And the corresponding feature space is lifted into a higher dimensional space because of less constraint. And in the higher dimensional space, it will be easier for the true signal set of the gamma to be orthogonal to its complementary set. So this means as nu increases, our irrepresentable condition can be easier to satisfy intuitively. And we formulate this intuition into our theoretical results that as nu approximates to 0, our IR nu approximates to the IC value in the generalized Lasso. But as nu increases, our IR nu can be less than the IC value. So this means as long as nu is large enough, our irrepresentable condition can be weaker than the IC condition in the generalized Lasso. Okay, so under this irrepresentable condition, we have the following theoretical results. That no false positive means the early selected features actually belong to the true signal set. And this can answer the previous question. On the basis of it, if the signal is strong enough, we can recover their signs. And L2 consistency means we can accurately estimate the values of the signals. To verify this theoretical result, we compare our method with the generalized Lasso in terms of AUC. And the AUC measures the goodness of feature selection in the solution path. So the larger value of the AUC means more probability for early selected features to belong to the true signal set. In both scenarios, when D equals to identity matrix and one diffuse Lasso matrix, our method can outperform the generalized Lasso in terms of AUC. And this can be explained by the last figure, in which the top horizontal line denotes the SC value in the generalized Lasso, which is larger than 1. And as nu approximates to 0, our IR nu approximates to the IC value, which is also larger than 1. But as nu increases, our IR nu start to decrease, and finally below the threshold value 1. So this means as long as nu is large enough, our irrepresentable condition is easier to satisfy than that of generalized Lasso. So in summary, we propose a dynamic approach by differential inclusion that generates a whole regularization solution path. And as iterates, more and more variables will be selected to be non-zeros, and earlier selected ones belong to the true signal set. So given this solution path, in the following, it is natural to ask when to stop in the solution path so that we can control the false discovery rate. And formally speaking, our goal is to determine the stopping time t to stop in the solution path. And if we go along this way, and before time t, among selected features, we can control the false discovery rate under the desired level Q, for example, the 0.1. And to see how this FDR control can be applied, we again consider the example of Alzheimer's disease, in which each node represents the volume of each brain region. And if two regions are adjacent, they'll be connected by an edge. And our goal is to select the edges with high contrast in terms of degree of degeneration of volume. So because in this regard, each of such pairs with high contrast may connect the degenerated region and the normal region. So this can provide a new perspective for us to identify the degenerated regions by looking their neighborhoods as a reference. After the FDR control by our method, as we highlight our selected edges, we can see that all of them will connect the region of hippocampus, which, as we recall, is responsible for the short-term memory loss, and it is believed to be the early degenerated region among patients. Okay, so next I will introduce our method to achieve this result. Our method is called split knockoff, which considers the setting of structural sparsity, in which we want to control the FDR of the gamma star. And after reformulation via variable splitting term, we have the design matrix of the gamma star. And what we do here is to create a copy matrix that mimics the covariance behavior of the X gamma. And we denote the copy matrix X as the knockoff copy. So the idea of our method is like this. For each feature xj, we create a copy x tilde j as a control. And we use the black box algorithm to assess the effect of xj on y and the effect of x tilde j on y simultaneously. And we compare their effects. As visualized in the following plot, the red dots and the dark blue dots denote the original variables in terms of their effects. And from the practitioner point of view, she cannot differentiate the red from the blue because she does not know the ground truth of which one is the non-null variable and which one is the null variable. But she can access to the additional behavior of the copy variables, which she can use to estimate the behaviors of original variables. And specifically, the non-null variables have larger effects than their copies. But for null variables, they have comparable effects in their copies. So this means in terms of the comparison score, which compares the effect of the feature j to its knockoff copy, we have the following properties. That for if the feature j is non-null feature, which has larger effect than its copy, the comparison score is positive and it has large magnitude. And if the j is null feature, which has comparable effect than its copy, then whether it is positive or not is like a coin flip. So we can refer to the information of the comparison score wj in terms of its magnitude and also the sign to identify the non-null features and control the FDR. Okay, so next, I will step into some mathematics to see how we control the FDR. And specifically, we order all variables in this fashion according to the absolute value of the W. And at each stopping time t here, we start over here and count down over here, and we select those features that are positives and have larger magnitudes. And we correspondingly estimate the false discovery proportion as the number of negatives over the number of positives. And we do this at each t. And we go down this way until the last time this proportion is less than Q. So this is how we determine the stopping time. And the final selected features are those positives and right to the stopping time tau. Okay, so to see how this stopping rule can control the FDP, which is defined as the ratio of null features, we multiply by a term and divide by the same term without changing the value of FDP. Okay, so, and we highlight some terms in blue. If I run our method by design, this ratio marked by blue is going to be less than Q, because this is how we estimate the false discovery proportion and how we determine the stopping time. So this ratio is exactly our estimation of the FDP at tau. So if I stop by design, it will be less than Q. Okay, so the FDP in this regard is no more than Q times this term, which I'm going to show that it will be less than 1. So in this regard, the FDP can be controlled under the desired level Q. Okay, so if we take a closer look at this term, which is defined as the number of null positives over the number of null negatives, it is roughly 1. Because for each null feature, as we remember that whether it is positive or not, it's like a coin flip. So it has equal probability to belong to the positive set or the negative set. But we must be careful because it stops as a random variable, random time. So to prove it, we show that this process is actually an almost supermartingale with the filtration of how many positive and negatives are left. So this means this process is non-increasing in terms of t up to the minor infinitesimal. So combined with the previous result, the FDR is no more than q times this term, which can be no more than itself at the very beginning due to the non-increasing property of the almost supermartingale. So finally, this term is roughly 1, because for each null feature, whether it is positive or not, is like coin flip. Okay. So in this regard, our speed knockoff can control the FDR theoretically. And as a verification, we conduct a simulation experiment in 3 scenarios of structural sparsity. And in all scenarios, we can successfully control the FDR under the desired level Q. And besides, in terms of power, the result of power, which is defined as 1 minus type 2 error, we can almost recover almost all the true signals. So in this part, we have introduced a dynamic approach for structural sparsity modeling, followed by the FDR control in this dynamics. And in the next part, I'm going to show that how we apply this framework to explore the structural sparsity in a deep neural network. And specifically, our goal is to learn the subnetwork, which has comparable test accuracy than the original dense network. And to achieve this goal, the old school backward pruning method adopts a 2-step strategy. The first step is training on an original network, and after that, it prunes on the trained network. So it is time consuming. And in contrast, our method can, guided by the differential inclusion, can forwardly learn the subnet coupled with the dense parameter W and the sparse parameter gamma. As visualized of our learning process, the dense parameter W undergoes a gradient descent flow on the original dense network. And it can self-inherit the nice properties of our parameterized model, such as in terms of optimization and generalization. And meanwhile, it can drive the sparse estimator to iteratively learn the important weights and filters from sparse to dense. Okay. So we can theoretically prove that this learning process has global convergence property, and also after we adopt the early stopping mechanism, we retrain the subnet given by the sparse estimator, which is the subnet, and we can achieve comparable results than their original dense networks. But more importantly, we found that the earlier selected features, as we zoom in, correspond to the contextual information. And this echoes the existing findings that ImageNet trained CNNs are biased towards the texture information. Although this texture information can improve the prediction power, but it is non-robust and it is unstable. So it will cause serious consequences, especially in risk-sensitive tasks. Sorry. So this is not what we want. So to resolve this problem, in the next part, we'll show how do we learn the causally semantic features to resolve this problem. And this is the direction I started to explore after I joined the Microsoft research. And before we start, I'm going to first introduce some basic knowledge about the causal inference. The causal inference studies problem like whether treatment is effective in terms of the disease recovery. And we must be careful because both variables can be simultaneously affected by a third confounder, for instance, the social economy status. So in this regard, the wheelchair people can at the same time afford the drug and also receive better treatment so that they can have better outcome than other people. So the presence of this confounding bias can make it wrong if you directly compare the people who take the drug and people who don't. To remove this confounding bias, we introduce an important concept, namely the intervention operation, which is denoted as dual operator. And the dual operator is equivalent to cutting the edge from the confounder to the treatment variable and setting its value to 1 or 0. So in this regard, the original generating process is broken and the confounding bias can be removed. So it is like a randomized control setting after intervention. And we can therefore define the causal effect as the average difference between the treatment and control groups. The result of this causal effect as a consequence of the intervention can help us to identify whether the treatment variable is the cause of the disease recovery variable. Okay, so on the other hand, if you want to calculate the causal effect under a certain situation, we do the counterfactual learning. The counterfactual learning means given the past observation which has already happened, we imagine what outcome would be if we took a different action under the same situation. So the counterfactual world is the same to the real world, except that we took a different action. If we directly compare the counterfactual outcome with the observed outcome, similarly, it can help us to identify in this certain situation that whether the treatment is the cause variable of the disease recovery. Okay, so in the next, I'm gonna first introduce our interventional method to learn the causal factors. And before we start, we first consider example of handwriting recognition dataset in which each number is colored, and there's a correlation between the color and digital label in the training set, because it is very likely for 0 to be colored as green and for 7 to be red. But in the test set, this correlation does not hold, or it is reversed. So this will cause a drop in terms of accuracy compared to that on a clean data set without color. But in contrast, our method can achieve comparable results than those on a clean data set. And this is because we have captured the causal factors. And if we visualize what we have learned, we generate a sequence of images as we interpolating the learned causal factors. So as interpolated, the generated images change from 0 to 7. Specifically, it can learn to remove the left part of the 0 and add a dashed line to form the 7. And on the other hand, for contextual features, the images change from green to red. So this means we can decompose those sorts of factors into causal features and contextual features. And during prediction, we can only use the information of causal factors so that we can have better generalization. To see how do we achieve this result, we first assume that image X, the input, is generated from latent components. For example, in the image in which the table is on the floor, these latent components include the information of texture and contour of the table, and also the view to take this picture, and the background information, for example, the floor and the wall. Besides, we assume that only a subset of these components contain the causal factors that are related to the object of interest. For instance, if we want to detect the table in this image, and the table, so the table is our object of interest, so the corresponding causal factors are texture and contour of the table. And in addition, we assume there is a correlation between causal factors and other non-causal ones. And this can explain why we can learn some non-causal factors during data feeding. If we consider the same example, the texture of the table and the floor are in the same room and they are consistent. So this means they are both determined by the people who decorate the room, very likely. So in this regard, these variables are correlated with each other. Okay, so we embed this assumption into the following causal graph, in which we denote the S here as the causal semantic features and D denote the contextual features. And both latent variables participate in the generation of the image X, and only parts of them are related to the causally related to the object of interest. And besides, there is a Sparse correlation between S and Z, which opens the path from the non-causal factors to the label. So if we directly feed the data, we can learn some contextual information. And this is not what we want. So to resolve this problem, we first ask ourselves that can the causal factor be identified without mixing other information? And we answer this question by first illustrating how the intervention can help to remove the Sparse correlation. And specifically, we first observe an image in which the dog is on the grass. And also we can access to the labeled dog. But we have never observed the dog before. So after roughly decomposing the image into the animal and scenery, we do not know which part referred to the labeled dog because we have never observed the dog before. So to figure it out, we imagine we want to see another intervened image in which the dog is on the snow. If the label is unchanged, we know that the scenery is not the causal factor. So this is the illustration of how the intervention can help to remove the spurious correlation. And also, this is an illustration of soft intervention to remove the spurious correlation. And what I mean by soft intervention is instead of assigning a fixed value to the variable, it assigns a different distribution from the original one. Okay, so inspired by this illustration, we propose to partition the original dataset into several environments with diverse correlation between S and Z. And this diversity in the correlation corresponds to diverse soft intervention mechanism on the latent variables. And the basis on based on this soft intervention, we have the following theoretical results. That as long as we can fit the joint distribution over X and Y on each environment, we can uncover the causal factor up to a transformation. And also particularly note that this transformation does not rely on the information of others. So this can answer the previous question that the causal factor can be identified without mixing other information. On the basis of this, we can also uncover the invariant prediction, which only uses the information of causal factors. So this can explain why we can generalize well on the colored handwriting recognition dataset. So according to our theoretical results, if we want to infer the causal factor S, it is sufficient for us to fit the joint distribution over X and Y on each partitioned environment. Okay, so what we do here is to reformulate the evidence lower bound in the standard supervised learning setting. And we propose to maximize the elbow, which is equivalent to optimizing the variational distribution and also maximal likelihood. After reformulation, our objective function is composed of three parts: the cross entropy loss for prediction, and also reconstruction and Carroll divergence losses. We can theoretically prove that our estimation method is consistent. And we further apply our method to the peripapillary atrophy prediction, which is related to many types of eye disease. In terms of AUC, our method can outperform baseline by a large margin. But also, as visualized, we can successfully identify the optic disc region in the eye, which is believed to be the lesion area for the PPA. Okay. So in addition to interventional method, next I'm going to show how our counterfactual method to learn the causal factors. Specifically, we consider the weakly supervised learning setting in which we want to detect the lesion areas of the breast cancer. And what I mean by weakly supervised is instead of lesion areas, the annotation of lesion areas, only the image and its disease label are given. And each breast image contains two sites, and which we denote the target site and reference site. To detect the lesion areas, we first ask the following counterfactual question: that we want to generate the version of target features without lesion areas, given the observation of the images of two sites. Okay, so if we directly compare the target features with lesions and the counterfactual ones without lesions, we can then obtain the lesion features, and this is what we want. So to answer this question, we propose, we leverage an important symmetric prior in the breast cancer, and this symmetric prior means if the target site is lesion on the region omega, then it is lesion-free on the reference site on the symmetrical area. So it can help us to remove the lesion area in the target site, because we can refer to the reference site, which is lesion-free. And on other regions that out of omega, we can refer to the target site itself. So this is our exactly our theoretical result mean after we formulate the symmetric prior into our causal modeling. Finally, in terms of type 1 error, our method can outperform baseline by 20%. And also, as visualized, the lesion area selected by our method can be much less redundant than those of others. Okay, so in this part, I have introduced interventional and counterfactual methods to learn the causal factors. In the final part, I will briefly introduce how the causality can resolve the fairness and robustness problems. For robustness, we first consider the example of regression problem in which covariance set contains the S1, S2, and M. And we highlight M here because its generation from its parent changes across environments. And due to this distributional change, if we directly regress on all covariants, we will get non-robust mean square error result as represented by the red curve. Generally speaking, the original covariance set is composed of two parts, the stable set and mutable set. Each variable in the mutable set is dependent on environment in terms of its generating process. To resolve these non-robustness problems, we propose to detect the mutable variable set and intervene on it. And this is equivalent to removing the spurious dependencies incurred by the mutable variable. Theoretically, we can prove that this predictor is invariant across domains. And also, more importantly, we can prove that it is min-max optimal in the sense that it can perform very robust under the worst case. And guided by this theoretical result, we propose a local causal discovery algorithm to detect a mutable variable and followed by the data regeneration mechanism to estimate this interventional distribution. So finally, in terms of mean square error, our method in terms represented by the blue curve can stably outperform others. And we further apply our method to the gene function prediction, that we want to predict the function of each gene. And we do this by predicting the cell counts if we knock out this gene. And different domains correspond to knocking out different types of genes. After learning the causal graph, our method can similarly achieve the minimum mean square errors compared to those of others. And finally, for fairness, we consider the health equity problem, in which the health equity is defined as the same chance for everybody to be healthy. And the equity is different from equality because we had to take into account different social economy factors among populations. And based on that, we can implement the methods for adjustment. And specifically, we work on the spine disease dataset, which was collected by Jim Winston, who worked his life to promote the health equity in the US. And this sport dataset, as we briefly called, is to study the effect of social factors towards treatment outcome. And in terms of the treatment outcome over time, we can observe that there's a large difference between the white people and other people. And this is a big social issue because there is unfair result treatment outcome among different races. And this is also pointed by Jim. So our goal is to analyze and reduce this difference as better as we can. And this problem is equivalent to reducing the causal effect from the risk variable to the outcome variable. And to achieve this, we decompose the total effect into two parts. The first part is the direct effect, which is due to some unknown reasons. And the second part is the mediation effect, which is the effect mediated by the social factors, for instance, the income. So the mediation effect is very important for policymaking because if this effect exists, we can accordingly adjust for social factors, for instance, in improving the income or working benefits to remove this effect. So our goal is to estimate the mediation effect for policymaking. And according to its definition, it is dependent on the interventional distribution. So to estimate it, an important issue is whether it is identifiable. And we can prove it by using the technique from the inducing path graph, and we can correspondingly estimate it as the joint distribution. So to verify this, our theoretical result and also the estimation method, we first conduct simulation on synthetic dataset in which we want to estimate the mediation effect and the direct effects. In each estimation, we use the horizontal color line to denote the ground truth value. And we run our method over 100 times. And for each time, we use the gray curve to represent our result. We can see that as sample size increases, our gray curves, our results can be concentrated around the ground truth value. And then we apply our method back to the sport data set, as I mentioned from the start. And we first detect the mediation factors as the income, working status, outcome at baseline, and BMI. And we can observe that our estimated mediation effects are comparable to direct effects. So they are both non-ignorable. And according to the mediation factors, we can correspondingly suggest improving the working benefits due to the income and working status, and also more aggressive treatment due to the outcome at baseline, and also calling for attention of healthy status due to the BMI. Okay, so in summary of my research, in high-dimensional statistics, we propose a dynamic approach via differential inclusion, and we prove its model selection consistency and FDR control. In the causal inference, we propose interventional and counterfactual methods to learn the causal factors, followed by the minimax predictor for robustness and the mediation effect estimation for equitable healthcare. In addition to my research papers, some of my work have been transformed into medical products and serve the first-class hospital at grade 3 in China. And for instance, the early prediction of Alzheimer's disease and microcalcification detection in breast cancer. In the future, I will continuously explore stable learning and causal inference to benefit the robustness and, more importantly, smarter and general AI to make the model have human-like thinking ability. Besides, I will focus on the statistical and dynamically modeling and its application for scientific findings, such as genomic analysis, drug discovery, social dynamics, and use ODE or PDE method to describe or find physical law. In addition, I'm also interested in proposing medical imaging-oriented methodology to benefit explainability and robustness, and also resolve the challenges from multimodality data and semi-supervised learning setting. And also, speaking of teaching experience and plan, I have previously engaged in teaching courses such as causal inference and statistical learning and probability and statistics. In the future, I'm willing to deliver my knowledge in the following courses, such as probability and statistical inference, machine learning, medical imaging, and mathematical foundations for AI and optimization. Okay, so this is all about my today's talk. Thank you for attending and listening, and I'm looking forward to your questions.
Thank you very much. It was a very nice talk. If you have any questions, you can either type them into chat. You can maybe just raise your hand, and basically afterwards you can ask a question, unmute, and you can ask questions, which will be fine. Maybe my first question, again, I'm not an expert in all those stuff you mentioned, but talking about this equity and so on. Let's imagine you have like these medical diseases and so on, and you can have many patients which don't have money to buy the high expensive drugs, right?
Yeah.
So what are the possible problems or benefits from the method? Benefits could be you can sometimes to adjust, make the policies and so on. But what could be somehow like the drawback of this approach? For example, if you somehow try to push some people from low income to maybe take medicines which are maybe cheaper, but maybe not so effective, could this happen?
Yes, and this could happen because the outcome, the people who have worse treatment outcome may receive worse medications, also pharmacy, and this is because of the income, the less income compared to the white people. So so if this effect exists, we can improve the income, and we omit some variables here, but it can emerge in the path from the mediation factor, for instance, income to the outcome variable. So yes, this actually the income may actually cause the worst medications, and we just omit here because the mediation, the social factors or income here can help us to make the policy making. Okay.
So maybe some related question for this one, like like in some sense, if you have this data set, you somehow say we have to create a model which will be somehow like equitable and so on. You somehow need to define what you measure, what you somehow mean by that, right?
Yeah, yes.
Yep. So it's somehow like still like somehow like biased by someone who will decide what to do, right?
Yeah, yes. And
Is this,
yeah. Yes, before the if given the data set, we do not know what variable is the mediation factors. So we must detect some the social factors, because we may think ahead that the education or some insurance, medical insurance may be the mediation factors, but actually during our detection they are not. And so we first should detect the mediation factors, and after that we estimate the mediation effect. If we find the mediation factors, the effect caused by the mediation factors is significant, we should accordingly make adjustments. And we have, if I may, I have some backup slides and to see our specific result on each variable. So for the mediation factor, we can observe that actually the BMI is the most significant, and the working status is also the baseline outcome is also significant. So this means for the other people, for instance, the Black people, they may have worse baseline outcome from the start, and so we should call for a more aggressive treatment. And also, according to BMI, we may have calling for attention of their health status.
Okay, that makes sense. Can you somehow try to discuss the project which you somehow did with the hospitals and so on? You mentioned a few of them as your past research.
Yeah, you mean whether they can be leveraged in the hospital?
Yeah, so you somehow mentioned that you somehow try to like work on something to help with the breast cancer and
yeah. The breast cancer is actually served transformed into a medical product. Yes, and also the lung cancer prediction and this macro calcification detection, and also the robustness. I didn't write it in this slide, but actually we are transforming the robustness problem in which I introduced earlier. That also we are transforming it to medical product.
So basically, like how this collaboration was happening, like did you try to talk to hospitals, or they approach you, or?
Yes, the hospitals, and such as but there are hospitals in China, and for example, the Peking University People's Hospital in Beijing, and also the Xinhua Hospital in Shanghai. Yes.
Okay, nice. So anyone else has any questions? I know some of us needs to go to different meeting, but still, if anyone has any questions, please ask now. Many of them already had to leave. Okay, if there's no questions, then thank you very much, and enjoy your evening.
Okay, thank you.
Thank you.
Thank you for attending.
Pleasure to meet you.